Yeah, so today we're going to talk mostly about mass spectrometry. And then we'll do a little exam-like exercise all the way at the end, where you have to combine infrared, mass spectrometry, and NMR to solve an unknown compound. Okay, let's get going. Okay, so some of the history. So Mr. Thomson, he got the Nobel Prize 1906, not for mass spectrometry, but for discovering basically that ions can be deflected by a magnetic field, right? So here we're going to talk about this more. We have basically two plates, and in between those two plates, we can accelerate charged particles like ions. So the ions get accelerated, you get an ion beam, and here they travel through a magnetic field and they get a deflection, and then they use this fluorescent screen to see these lines of these ions on the screen. So this was kind of a first finding. We'll get back to that. That has to do with the Lorentz force. The Lorentz force, okay, we'll explain later. Okay, so here's the list. Later, so this was used to discover that there are actually isotopes for other elements than radioactive ones. I mean, people knew kind of that for radioactive things, the atom falls apart and there must be different, elements and isotopes, but up to that point, basically this was not very clear. And then later there have been other two Nobel Prizes for other more specific mass spectrometry techniques, especially in 2002 for soft ionization. So there are a range of techniques we'll go through. One is called AZ and one is called MALDI. And they have become very important in chemistry and in biology. Okay, this is the periodic table. You knew that. And so we have a lot of elements, and usually in the periodic table, you have the atomic number and you have the atomic weight. So the atomic weight, is that the weight of one atom? Or what do you think it is? Yeah. It's actually an average, right? It's an average of the weight. So if you do a macro scale experiment, let's say I'm going to weigh magnesium chloride, then I can calculate the molecular weight by using these atomic weights, and then I can weigh my sample. I can divide by the molecular weight, and I get the number of moles. This is how we normally do it. But if you go to mass spectrometry, we will actually see that you can see the different isotopes of elements, right? Carbon has carbon-12 and carbon-13, like we saw in NMR. But a lot of elements have different isotopes. So we'll see how these isotopes have different weights and how their distributions lead to the atomic weight. So here an example. So a lot of elements are monoisotopes, which means there's only one, maybe it's 99%, basically one isotope, like fluorine, sodium, phosphorus. Again, these ones are NMR active also. And then you have elements that have two isotopes. For example, chlorine has two isotopes with different weights. So now we have the mass here. And for mass, you can have all kind of units. It's wonderful, but the easy part is they're all the same, right? So one U or one A mu or one Dalton or one mu, it's all the same. It's defined as 1/12 of the mass of carbon-12. Okay. And that typically, if you show a mass spectrometry graph, they show what's called the nominal mass, which is a whole number. But usually the real mass is 35 point something, 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 right? Okay, and so abundance, just like in NMR, is important in mass spectrometry, right? So you can see that, for example, for bromine and chlorine, you have this natural abundance that looks like this. So for bromine, the two isotopes, 79 and 81, they are almost the same natural abundance. And they're spaced by 2 units, whereas usually for most isotopes, they are spaced by 1 unit, right? There are very exotic ones, like xenon has a lot of isotopes with this distribution. Okay, so that's important to keep in mind. Carbon also has isotopes, right? So we have carbon-12, which is basically around 99%, and carbon-13 is around 1%. Carbon-14 is actually radioactive, right? Which is present in very small quantities, and it decays with this rate. So if we think, okay, we are going to make a molecule, we have 99% of the carbons are carbon-12, and 1% is carbon-13. So if you have molecules that include more than 1 carbon, the probability that you will find a carbon-13 will be higher, right? So the main peak, let's call this the PM. So this is the probability that you will have, let's say, only carbon-12, is if you have a small molecule with, let's say, 5 carbon atoms, that is very high, and you have this 1% chance. So if you have 5 carbons, then, I mean, my statistics not that good, but let's say it's 5%. And actually, that's true also if you go to molecules that have more carbon, so C60, for example, the Buckminster fullerene, this football of carbon, you see a much stronger distribution of peaks. So what does that mean? So the largest peak is still where all the molecules, or sorry, all the atoms of carbon are carbon-12. So I have carbon-12 times 60. Then here, the next peak, I have 1 carbon-13 and 59 carbon-12. And then here I have 2 carbon-13, 58, 3 carbon-13, 57. So since they are in the same molecule, and in mass spectrometry, molecules, they fly as one piece. Usually they get also fragmented, but we'll get back to that. So you can actually estimate the number of carbons. It's not very accurate, but more or less the number of carbons, you can estimate it by the ratio of those 2 peaks. So PM plus 1 is the next peak, let's say. This ratio, if this, for example, here, this peak has a 20% intensity compared to the main peak, I can estimate that there are about 20 carbons in that molecule. So there's some mathematics behind it, but that's the basic rule. So you can just look at the distribution of carbon isotopes, and that actually tells you how many carbons are in that molecule. Okay, so that's interesting. Halogens, like we said, bromine, they have these 2 isotopes. So if you have more than 1 bromine in your molecule, you will see a certain distribution of isotopes, the same for chlorine. So actually that can be a signature in your mass spectrum that you have the presence of a halogen. So if you see a peak that is spaced by 2, then you can maybe say, okay, maybe there's a halogen in my molecule. Okay, let's look at the atomic mass in more detail. So if we have chlorine, this is what is, so I copied from the periodic table the atomic weight here. And so it's 35.4528 U. And as we saw a little bit before, chlorine is a diisotope, so of chlorine 35 and chlorine 37. So again, these are the nominal masses and the exact masses. And the abundance is 75% chlorine 35 and 24% chlorine 37. Now, in mass spectrometry, for some mystical reason, they always call the most abundant peak, they put that at 100%. Right? So if we go back here, let's say I have some peaks, they will always set the highest peak to 100%, and the other ones scaled down from that. So they call that the relative abundance. So the largest one, they call it 100%, and in this case, the second one is 32%. This is just a bit confusing, but okay, let's use that. So if we multiply the abundance with the exact mass of that isotope, so I do 100% times 34.9 plus this abundance times 36.9, divide by the total, 100 plus 32, I get 35.45. Right, so as I said in the beginning, the relative atomic mass that you see in the periodic table is actually a distribution of masses where you take the average according to the abundance. Okay, if there's any questions, please interrupt. So in mass spectrometry, we have different steps, and we'll go through those in a while. But basically, first you want to make an ion, right? If you don't have an ion, I cannot use electric or magnetic fields to manipulate the ions. So I need to ionize my compound. And I can do that using electrons, I can do that using a laser, or I can do it from a spray of droplets. Then when I have my ion, I can accelerate it, and then I can detect it in different ways. Okay. Ionization. So what is ionization? You know this from other spectroscopy courses, I guess. But the ionization energy is the minimum amount of energy that you need to put in a molecule to form an ion that is also in the ground state by ejection of an electron. So we have to kick at least one or more electrons out of the molecule, and it becomes ionized. So how does it work? Here I have my molecule. Let's say it's in the gas phase, and it flies through this electron beam, right? So these are accelerated electrons. They hit the molecule, and two things can happen. The simplest one is non-dissociative. So you have the molecule, you kick out one electron, so you end up with 2 electrons. And I now have a positive charge on my molecule. And we'll see it can be a cation, or it can be a cation radical, or a radical anion, or different solutions are possible. Or the molecule dissociates or fragments, as it's called, and it loses a fragment and electrons. And there are certain rules for how things fragment and when that happens. But the main result is, okay, I have my molecule, I add an electron, and I kick out the original electron and one more electron, and I get this radical cation, right? So this just means one electron has been stolen from the molecule. But you can have also multiple charged ions. So when we go to towards the end of this class, we'll talk about soft ionization. And there it's very usual to have 20 charges, 100 charges on the same molecule. This is typically on biomolecules. So if you have a protein have many amino acids, they have groups that can be ionized. So it's not uncommon to have 20 charges, 50 charges on the same protein. Okay, so we have made our ion, and now we're going to accelerate the ion between 2 plates. So we have basically the ionization beam just before here. There's a small hole, and the ion will be accelerated through this hole over here, right? So I have a certain distance, I have a certain potential between those 2 plates. So use quite high voltage, 20 kilovolt, can be even higher. And we're going to calculate the speed at which this ion comes out of this acceleration. Okay, So we can express the electrical energy as the charge of the ion times the voltage, so the difference between the two voltages of the two plates. And this is the integer number of charges, so 1, 2, 3, 4, 5. And this is the charge of an electron, which is a constant. And we basically say that the electrical energy is fully converted into kinetic energy. So kinetic energy, you notice it's half mv squared. So we make those two things equal and we solve for velocity. And then we see velocity of the square root of 2 times the charge of an electron times the integer charge times the difference between these two voltages over the mass. So let's take back our example of C60 of the fullerene. So fullerene has this mass, and let's assume here it has a single charge. Okay, so this is one electronic charge times this voltage we just saw on the slide. So it comes out at 72 kilometers per second, which is really fast, right? Way faster than the sound barrier. So you can have really, really fast flying ions in mass spectrometry. Okay. So now we have this hugely fast flying ion. How are we going to measure the mass of the ion? And so the first thing is that we don't really measure mass directly. We measure a ratio, which is mass divided by the charge, so 1, 2, 3, 4, 5, 6, 7, of the molecule. So if you look at the mass spectrum, on the x-axis, you will see m over z, okay, mass over charge. And on the y-axis, it will be proportional to the abundance of the ion. And that does not directly correlate sometimes with what you expect. So there are reasons why some ion fragments are more favorable, some ions are more difficult to form. So it's not always an exact science in terms of the intensity of the peaks. Okay, so this is kind of a joke towards thermodynamics. So they have the zeroth law of mass spectrometry. This is not really a real thing. It's more a joke in this book, is to call it always mass spectrometry and not mass spectroscopy, right? So because there's no light involved in mass spectrometry. So never say mass spectroscopy because some people will get angry. Okay. So now we are going to look at this ion. So here it's the same kind of drawing. I have my ion that is being ionized, and I have two plates that have a voltage difference over them, which lead to acceleration. And now I have these crosses. That's actually a magnetic field that is going into the blackboard, right? And you can use then, I think I have it on the next slide. No, I don't, wait. You can use the Lorentz force. So this is the right-hand rule. You've probably seen this somewhere. It's like the physicist ghetto sign, like this. Okay, so using the, I have it on the next slide, the Lorentz force, you can actually see that if the field is going into the blackboard or into the screen, I will get a deflection to the right, and the ions will make a half circle, and they will end up on the detector. And if ions hit this detector, it creates a current, and I can measure this current. So you can imagine that this is kind of an analogy with racing. So if you are lighter, so someone on a motorbike is lighter, they will turn sharper at the same speed than when you are heavier. You will end up more here. So by changing the voltage on the accelerator, I can actually choose which ions end up on the plate and which ones don't, which gives me a way to measure my different ions. Okay, here it is, right? So the force, the Lorentz force is along your thumb. The magnetic field B is your index finger, and the electrical current. So in this case, the ions are along here. And then it depends if your ions are positive, it will go in this direction. If they're negative, it will go in the other direction. Right, so let's go back here. Okay, so now you take your finger, right? So force is your thumb, magnetic field is in the board, and then the ion source is, let's say, going up, so like this. So the force is to the right. So this means these are actually positive ions, and they are deflected to the right, okay? So you can calculate this, or you can at least determine the direction using the right-hand rule of the Lorentz force. So in another way is to detect by the time of flight, it's called. And so more modern mass spectrometers, they typically use time of flight, or TOF, to determine the mass of the ion. So here, let's say we have a sample and we have an ionization event, in this case by a laser. We'll get back to that. So we have an ionization event, we have an acceleration, and then we will just count how many ions arrive at what time. These are very short times, right? So as I showed you for C60, the speed is, you know, above 70 kilometers per second, so really fast. So there's a very high time resolution. And so smaller ions will arrive first, and then larger ions with higher mass, they will arrive later. So by using a super fast detector, I can just count how many ions arrive at each time, which I can directly translate into the masses of those ions. Well, the mass, the m over z of that ion. Because if I have an ion which is larger, but it has 10 charges, it will be accelerated more, and it will arrive first. Right, if we go back to the equation for the velocity, right? So the velocity scales with the square root of the number of charges. So if I have, you know, 10 charges, my velocity will be square root of 10 higher than when I have 1 charge. So that's the tricky thing, again, to repeat mass spectrometry, you measure m over z, mass over charge. Okay, so modern instruments use typically time of flight to detect the mass, the m over z of the ions. So this is a typical spectrum, right? X-axis, mass over charge, m over z. And here I have relative intensity, where it's always scaled to the largest peak, which is 100%. And here I have the molecular ion, so this M radical cation. So this is the molecule with 1 electron kicked out. This is the mass of my molecule. So usually the peak with the largest m over z will be the molecular ion, right? So here I have methane. Methane has a carbon. The mass of carbon is 12. Nominal mass, the mass of hydrogen is 1. So 4 plus 12 is 16. Hey, we have 16 here. That's great. Then you will get fragmentations, which we'll get to in a lot of detail. But basically, an electron hits this bond, and it can actually lead to homolytic or heterolytic cleavage. So if we lose 1 hydrogen, we lose 1, so we go to 15. Sorry. And we can lose more hydrogen, and we end up all the way at carbon, right? So this is the fragmentation. We'll get back to that. So first, a bit the older implementations, but they are still used a lot. So in the ones that are called EI, which is electron ionization, they are ionized by electron beam, can be laser, can be droplets. So we're first going to go more to this. And this is a kind of overview of all the, well, not all, but the most important mass spectrometry techniques. And there is a really large difference between how hard the ionization is. And you'll see that if you do hard ionization, you also get a lot of fragmentation. Whereas if you do soft ionization, then actually you don't destroy the molecule so much. So you can imagine if for methane, I already get 6 peaks, if you put a protein, you will get 1,000,000 peaks, and I don't know what to do with that anymore, right? So for larger biomolecules, you want to go to these softer techniques. Okay, so let's work a little bit on the interpretation of mass spectra. So the first thing you want to do is look at the molecular ion peak, right? This is the one usually with the highest m over z. And then you have to check, okay, from the molecular ion peak, there will be peaks with lower m over z. Are those losses, you know, the things that fall off of this molecule, is that actually reasonable or not? And there are certain rules for that. So there's the even electron rule, which we'll get into, and there's also a nitrogen rule. Okay, we'll get back to what that means. And then you can also consider the isotope patterns, right? So if you have a halogen, then you should probably find a fragment that has a mass difference of 2, because the isotopes of bromine and chlorine have a difference of 2. So that should be still there even if you have fragmentation. And then, of course, just like for NMR and for infrared, there are databases. So you can compare what you find with online databases. There are also some simulators to simulate the fragmentation pattern, but they are a bit more complicated, I have to say. Okay, so step 1, you have to find the molecular ion. So that's this radical cation. And so it has the same formula as your molecule, and they only differ by 1 electron. So the mass, the mass of an electron is almost nothing, you know. So your mass that you measure, m over z, will be basically identical to your molecule. And it can be positive. That's the most usual case if you use electron ionization. And it can be also negative. So in MALDI, you can actually choose if you create cations or anions, and some compounds form cations easier and some form anions easier. So you can actually choose that. But for the moment, we are just going to consider positive radicals. And the nominal mass, right? So the highest peak you will see is the mass considering all the most abundant isotopes of that atom, you know, of the atoms in the molecule. So when you calculate the mass of your molecules, you have to consider the most abundant isotopes first, because that will be the most intense peak in your mass spectrum. Okay, so back to methane. So we depict it like this, you know, methane plus an electron, we kick out this electron and 1 more from methane. So we get this methane radical cation. But let's look a bit closer. So if we draw, so I draw a bond not as a stick, but as 2 electrons, right? So this is just a normal sigma bond. And so I get electron ionization. One of these 2 electrons is kicked out. This can be either the one closest to the hydrogen or the one closest to the carbon. So I get this structure. And these are the different ways people in mass spectrometry write these ions, right? So I can write it like this, or just like this. Okay, so back to methane. So this is the same spectrum I just showed you before. So the molecular ion is 16. We have these different events that are possible. And from this first ionization, we can get fragmentation. So we're going to break the sigma bond, and we get this methane cation, well, CH3 cation, and hydrogen radical, right? So 15 and 1, again, because electrons don't weigh anything. Or we can split like this. So we have the radical on the CH3, and we have a proton here. Again, this gives you the same masses, so you can actually not distinguish those two. Other than fragmentation, you can also get rearrangements, right? So rearrangements are a bit more complicated. We'll get into that. So here we make a kind of carbene radical cation and H2. So we also have 14 and 2. Okay, so here it is 14, and then I can get further fragmentation events. Okay, so let's check if the fragments that we lose are reasonable. And so there's a rule that is called the even electron rule, but you can also call it the odd electron rule. Basically, it says if you have odd electron ions, right, they can eliminate either a radical or a neutral species. But odd electron ions, right, will not usually lose a radical to form an odd electron cation. Okay. In other words, successive loss of radicals is forbidden, and then I put a star because, of course, there are some exceptions, like basically everything in chemistry, there's always an exception. But basically summarized, these are the rules. So if I start from an odd number electron, right, the sigma bonds have 2 electrons, so it's even. But if I kick one out, I have an odd number of electrons, and so that can break into an even number, so a cation and a radical, or it can stay odd and kick out a neutral molecule. The same for even. So an even number cation can give rise to a cation and a neutral fragment, but it cannot give rise to an odd fragment and a radical. Okay, we'll get to examples. There we go, methane again. So if we look at methane, this is the molecular ion. It's an odd number ion, right? And I create an even number ion plus a radical. So this is allowed. That's this one. Okay, here, the same ion, I create CH2 radical cation and H2. Is this allowed or not? Some people say yes. Yes, it is allowed, right? Okay, this fragment, CH2 radical cation, and I produce C, just carbon, and H2. We look, yes, that's the same. You know, it's an odd number, creates an odd number plus a neutral. So that's allowed. Same fragment, you make CH plus a radical. Yes, it's also allowed. Lastly, CH3 plus, so it's an even number cation. And we're going to do this one. Yes, that's also allowed. But for example, if I would have this fragment, I cannot have, for example, the loss of hydrogen radical. You know, that would be this rule, where I start from an even number ion, and I would have to make an odd number ion plus H radical, and so that's not allowed. Okay, so those are the rules. Let's look at some examples. So here we have iodomethane, right? So of course, iodine has a quite large mass, as you know, and I see the molecular ion peak, which is the mass of the entire molecule, right? So 142 is the molecular ion. And then let's look at the different fragmentations and rearrangements that can happen. So the first possibility is that I cleave this carbon-iodine bond, right? So I kick either the left or the right electron out. So here the left one is kicked out. I have a CH3 plus fragment, and I have iodine radical, which is 127 and 15. So we see here 127 and 15. So here, if you look naively to the spectrum, you could think, oh, 127, 128, it's maybe an isotope. But actually, iodine is a monoisotope. So this is not an isotope peak, but it's actually from this fragmentation pathway where I get a rearrangement and I make HI radical cation, which has a mass of 128. Okay, so sometimes you think things are isotopes when they are not, so that can be a bit confusing. Okay, so for the halogen ions, they also follow these electronegativity series. So the intensity of these halogen ions, they will be lower when you go more to more electronegative atoms because they are harder to ionize. Okay, so here iodine is a very intense, so these fragments, 127 is a very intense peak in the mass spectrum. Okay, let's look at acetone. So acetone is here, it can get ionized. So for example, we kick an electron out of this bond and we will get this alpha cleavage, right? So we make this ion here with mass 43, that's this one, and the CH3 radical, which is here. So this is relatively simple to analyze. Okay, butanone, that's here, right? So the molecular ion peak is 72. Then we can get alpha cleavage either here or here. So if we get alpha cleavage here, we get CH3 radical, which is 15, that's this one. Or we get this fragment, which is 57. So we see that here. Or we can get alpha cleavage here, and then we get C2H5 radical, which is this one, 29, and this fragment 43. Okay, which is the most abundant in this case. You can get also other fragmentations, right? So here we get CH3 plus and the same 57 fragment. And here we actually get the same fragmentation pattern. Okay, so if you are looking at the molecular structure, and we'll see that for certain families of molecules, you have typical fragments that are reoccurring. So if you look at the mass spectrum and you see certain masses, a distribution of masses, you can maybe say, okay, there must be this type of functional group inside the molecule because I see these fragmentation pattern. Like, for example, in this amine series, okay, I'm just reminding you of the atomic masses of the elements, right? So nitrogen is 14, the most abundant. So we have this, this compound, which is actually, it's an organic base used in synthesis quite a bit. And we can actually, so we see the molecular ion peak is 101. It's this, because we have nitrogen 14, carbon 12, okay, and then hydrogens, you sum them up, you get that, 101. And we can get fragmentation of this sigma bond, so we can get loss of one hydrogen, which gives you 100. We can get cleavage here, so we cleave a CH3 off. We have 86, and we can cleave also a C2H5 off, and we get this loss. But if you see this, these ions, they will be reoccurring in all kind of compounds that lose ammonium ions. Right, so ammonium ions have these masses, okay? Again, nominal mass and high resolution accurate mass. And you see that these fragments are, let's say, characteristic for ammonium ions. So if you see those, you can say, okay, probably there's some nitrogen compounds going on in my molecule. Okay, then there's also a nitrogen rule, which basically says that if your compound has an even number of nitrogen atoms, so warning, even can also be 0. But okay, if you have an even number of nitrogen atom, the molecular ion will have a nominal mass which is also even. If you have an odd number of nitrogen, so you have 1 nitrogen or 3 or 5, then you have an odd numbered nominal value of m/z. Okay, so let's look at some compounds. So methane, acetone, chloroform, fullerene, they have no nitrogens. So their mass is even, right? These are all even numbers. Now, if I have compounds with 1 nitrogen, ammonia, acetonitrile, pyridine, then the mass is odd, right? 17, 41, 79, 101. And if I go again to an even number, like urea or triazole, the mass becomes even again, right? So it is an indication, but warning, it does not mean that if you see an odd m/z, that it always has a nitrogen atom, right? So it's not 100% foolproof, let's say, but it's at least it's a good first indication. Okay, some other typical ions. So we can look at oxonium ions that are lost here. So it's CH3 oxygen plus, or C2, C3, C4, C5, etc., etc. So you can see again that you get typical fragments, 73, 59, 45, 31. So if you see this progression, then you can say, oh, maybe I have some oxonium groups in my molecule, which is again an indication. But you know, in practice, you would have some kind of handbook with fragmentation patterns, and you would look through that handbook, because it's it's difficult to memorize all these things. Okay, so let's consider also the isotope patterns. So here we have bromo-octane, and we can get fragmentation along the different bonds. But we also have to consider what I said in the beginning, that bromine has 2 isotopes, right, with almost the same natural abundance. So if we look at the fragmentation pattern, we get, for example, peaks that are spaced by 2. You know, so you see that in, let's see, in these fragments, I still have a bromine, right? So here I have a bromine, here I have a bromine, here I have a bromine, here I have a bromine. And you can see that there is 71, and then 69, 57, 55, 43, 41, okay? So you can actually see, if you see fragments and you have 2 very intense peaks that are spaced by 2, it is an indication that you have a bromine or a chlorine. Okay, so let's look at this fragmentation pattern. Okay, we get sigma bond cleavage at different positions, right? So here, 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 here. But we can also have a weird rearrangement. So if we get ionization here, we can actually get cyclization, and you get this 5-membered bromine ring, which has this mass. Again, the 2 isotopes, because I have bromine 79 and 81. Right, so I get, and this is frequently observed when you have alkane-based bromines, you will get this cyclization quite frequently. So this is a kind of typical fragment you will encounter. Okay. So, sorry, this box should actually be here, but let's look at some softer ionization methods. And so this is kind of an older one. It's called fast atom bombardment. I don't think actually it's used anymore, but okay. What basically you do is you have a beam of xenon atoms, right? That is accelerated, and they hit your sample, and that leads to what's called sputtering. So sputtering just means that little fragments and ions will fly out. And this can be a solid, or it can be a liquid, but a very, very high boiling liquid, because mass spectrometers work under vacuum. So you cannot have any low boiling solvents in your machine, or that will be an issue. But basically your beam hits your sample, you create all kind of things, cations, anions, neutral fragments, larger fragments, smaller fragments. But basically there is usually quite a bit of fragmentation still. This is the, let's say, latest generation techniques. So it's called soft laser desorption. So we're going to ionize using a laser. So you mix your sample with something which is called a matrix. And so this matrix is usually some kind of polymer or something like that. So you have basically a majority of your substance on a plate is the matrix, and then smaller quantities you have your molecule. And when the laser, typically this is UV light, the laser hits the sample with a pulse, and that is absorbed mostly by the matrix. Then it flies into the air, it gets ionized, and it will also ionize your compound. In this case, it's a protein. The protein gets charged. Then, because it's charged, it gets accelerated. It goes in the detector, which is a time of flight detector, and then that's transformed into my mass spectrum. So here I see the M/Z values. You can see they're very large, because proteins have high mass, right? And you can see, for example, I have the molecular ion, so the whole protein with 1 charge, but I can also have the same protein with 2 charges. So I get 2 peaks in my mass spectrum for the same molecule, which can be confusing sometimes for large molecules. Also, things that are quite common is dimers. So I have 2 times the same molecule that stick together. So you will actually see the double mass of my protein. Okay. Actually, when you are doing it in high resolution, you can, this is not very high resolution, but when you have high resolution, you can actually look at the isotope patterns of that single peak. And if the isotopes are spaced by 1, that means you have 1 charge on your molecule, because M/Z increases by 1. If the isotopes increase by half M/Z, that probably means that you have 2 charges on your molecule. So you can actually looking at the M over Z values of the isotopes, you can see what is what. Okay, let's go to MALDI. This is a very popular method. So it's the same. It's a soft laser desorption ionization with a matrix. So it's called matrix-assisted laser desorption ionization, MALDI. And same idea. So I have my sample, I have my UV laser, I get ionization, acceleration, time of flight analysis, and then I get my mass spectrum. And let's look at an example. So this is a very challenging gummy bear sample. So we take a gummy bear and we put it in water, okay? And then we take a very tiny bit of this water and we mix it with our matrix solution, which is another polymer, which is easily ionized. And then I will put a drop of this solution on the target plate. So this is usually a metal plate. It has little edged rings, so you know where to put your drop. You put your drops, it dries out, right? So you have a solid. And then this you put in the MALDI machine, and you can have a little gun where you can aim. That's actually quite a lot of fun. So you see a crosshair, and then you press a joystick, and then pew. You press the laser here, and then you see something like this, and then you're very confused. Okay, but here, so I have my M over Z, I have my intensity, and I see a lot of peaks, right? And this, again, this can be due to fragmentation, or it can be due to the fact that your molecule can have multiple masses. In this case, this is due to fragmentation. But we'll look at an easier example next. So this is, I think, now the most popular method for proteins or for any molecules, because it's very soft. You know, you don't use lasers, you don't use electron beams to hit your molecules, but you just have a small spray, right? So I have my sample being sprayed here, and I have an acceleration over here. So it's very soft. You get first small droplets, and they go progressively through higher, to chambers of higher and higher vacuum. So they evaporate, and at the same time, they get ionized. And so it's very soft. So this was Nobel Prize 2002. So you have very soft ionization, and you have very high M over Z. So for example, I have a protein in solution. It goes in this sprayer. The droplets get smaller, 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 smaller. Eventually, there's no more solvent. I only have ions of my protein. As you can see, they have huge numbers of charges. So they get accelerated a lot, and then I get this. So now you see you have, again, a lot of peaks. But what do you notice in those peaks? Is that the spacing gets larger, right? So actually what's happening, this is all the same molecule. It's the same protein, but I can get a lot of charges, right? I can get 30 charges, 40, 50, even more than 50 charges. So this is every time more, right? So this will be 30, 31, 32, 33, 34, 35, 6, 7, 8, 9, okay, 40. Right, so every time it's one more charge, and it gives a distinct peak in my mass spectrum because they arrive on the detector at different times, right? Different ion, M over Z has a different acceleration, has a different arrival on the detector. So then now with modern software, you can take this whole very complicated M over Z spectrum, which is basically redundant, right? It's the same peak over and over and over again. And I can deconvolute it into a single peak, which has then molecular weight. Okay, so that's called deconvolution. So in the end, after I deconvolute, I just have one nice peak, which is my molecular weight of my whole protein. So this is again a bit in more detail. Just like in NMR, you can have different resolutions, right? So low resolution MS or high resolution MS. It looks kind of the same. You would think, okay, who cares about the difference between this or this? Because this is M over Z, so it's the same molecule. Actually, this is a mixture of 3 different proteins. So by, if I give you this spectrum, it will be very difficult for you to figure out what's going on. But thanks to computers and deconvolution, we can now convert this into this. So we convert M over Z to mass. And then we see we have 3 nice peaks for these 3 proteins, myoglobin, cytochrome C, or ubiquitin. And if we zoom in on this peak, this one here, you can see the difference between low resolution MS. So we get all the isotopes are smeared together into a single peak. Whereas in high resolution MS, we can actually see the isotope patterns. Right, so that's nice. That's a really big difference between those 2. Okay, I suggest we summarize. Okay, so for mass spectrometry, it's a very nice method to get the molecular weight of your compound, and that again can help you get started on your molecular formula. Right, in the last class I said first thing you should try to do is try to get the molecular formula of your compound. Can be with elemental analysis, but as we commented, that can also be the double number of atoms, but okay. So elemental analysis and MS together, you already get a first idea of what your molecular formula is. You can look at the typical isotope patterns, right? So do I have a bromine? Do I have a chlorine? Then I will get this typical isotope splitting by 2 molecular weight units. You can look at fragmentation to find typical groups, oxoniums or other types of groups. And definitely you want to use MS together with other spectroscopic methods, as we said last time. Okay, so we'll do one problem set like you will get on the exam. Okay, I'm sure you know you have access to the exams of previous years, so it will be something not too crazy different, even though it's the first year I'm making the exam, so might be a little bit different. But right, so what are the steps you need to do to determine your molecule? And it's not, you should not necessarily do things exactly in this order. I wrote iteratively, right? So you can, depending on the information you have, you will start at different points. Maybe you first see something, very characteristic in the NMR, so that already gives you information, then you go back. But typically you will try to go more or less in this order, right? So the first thing to do is to look, for example, at the elemental analysis or at the molecular ion peak of your mass spectrum and try to determine your molecular formula, right? So in the mass spec, you can look for isotopes, you can look for fragmentation patterns. Is the molecular ion odd? That means there's an odd number of nitrogens. That's already an indication, but it's kind of vague, you won't be able to determine any molecule. In the infrared, so in the past exams, there was usually some small table with, vibrations and where they are. So, if you forget where the, OH stretch is in infrared, it's not a big disaster. I mean, try to still know more or less where you have to look, otherwise it will be a mess. And so in the NMR, so once you have identified maybe some functional groups or at least some typical stretch vibrations, you can go to the NMR. You can try to do a count of the protons, look at the integrals, look at the chemical shifts, and then try to iterate through these different points of information to see, can you assign some fragments, you know, the molecular formula, and so on. But always also keep in mind that, you know, compounds can be chiral and compounds can have different isomers. So just keep that in mind. Okay, yes, question.
Yeah, I'm looking at the mass, right? Or what should we do?
I mean, mass, of course, is a good indicator, but
why, when you say, because I forgot to ask you the question before, when you say all molecular ions, why we talk only about nitrogen and not the other atoms?
Yeah, because I mean, so most of the other ones, you know, give you an even chain. So if you have one more carbon or less, it's 12 different, right? But it's just only for nitrogen, it really makes a difference. So for most other atoms, the total nominal mass stays even. But if you have a nitrogen, it becomes odd. But it's not 100% bulletproof, so it's just an indication, right? But if you have an odd mass, it means there's an odd number of nitrogen atoms, so either 1 or 3 or 5. If the mass is even, then there's an even number of nitrogens, which can be 0, but can also be 2.
Okay, so nitrogen is the only mass, the odd mass.
Well, yeah, nitrogen-containing compounds, they usually, when they're odd, it indicates there's an odd number of nitrogens. Doesn't mean that there's you know, no nitrogen, or it just says something about the number of nitrogens. So again, like if the mass is even, it does not mean there are no nitrogen. It means there's either 0 or 2 or 4 or 6.
My question was, why nitrogen specifically?
Because of its mass, yeah. So just randomly turns out to be nitrogen. There's no real reason other than its masses that makes it uneven. Okay, so let's look at this information. So we have the electron ionization MS with the molecular ion peak. I have an NMR spectrum, and I have infrared. And now what? Okay. Where do you start? Anyone has any ideas?
The first thing to do is to put the formula of our molecular function.
Yeah, so we can look at the MS, and we see that the molecular ion peak is 70. Okay, so okay, that's one point of information. Then let's look in the infrared. So if you look up the table, okay, this one is in the class on infrared. We can see, so we have a vibration. Okay, it's difficult to see, but it goes, basically this is 3,500. It goes even above 3,500. So if we look in this thing, we are all the way at this end. And really the only thing that gives a broad signal, because this is quite broad, right? This is not a sharp peak, this is a very fat peak here. So that indicates there's an OH stretch. Okay, so maybe we have an alcohol, potentially. Then if we look in the NMR, we have a singlet here. And as additional information, it's written that this singlet disappears when you add a drop of D2O. So in the last class, we saw that if you have compounds that can have deuterium exchange, that signal disappears, right? So if we have OH plus D2O, right? So we can get deuterium exchange. The alcohol exchanges with water, it makes OD. OD doesn't show up in the NMR because it's deuterium, it's not hydrogen. So that peak disappears. So based on this infrared and this peak, we can definitely say, okay, there's an alcohol in our molecule. What else can we say?
COOH has also
Right. So how do we know it's not an acid? Okay. So we would look, so the CO stretch is at 1700. Right, so 1700 is, sorry, I cannot point to this. 1500, 16, 17, 17, there's nothing. So infrared, yeah, so it's not only the peaks that are there, it's also the peaks that are not there. So there's no peak at 1700. So I don't have a C double bond O stretch. So I know, that's a good question. It's a good question. So I know I don't have an acid, but I have an OH stretch. We could also try to look for a carbon-oxygen stretch, right? If the alcohol, let's say the alcohol has to be attached to something, it's probably CH2, right? The simplest thing would be this. So I have to have a CO stretch. CO stretch is between 1000 and 1300. Yeah, I have some stuff here, right? So, okay, that could be this. This looks kind of sharp, so maybe, maybe not. What else can you, okay, let's look at the NMR. What do you see in the NMR? Let's start from the downfield. So the most left thing is what? Triplet, yes. So we have a triplet, we have a singlet, which we already said is probably the OH, right? Then what is that thing? Sorry, I'm not tall enough. Yes, it's a triplet of doublets. And then we have another triplet. Okay. What else do you notice in these let's look at this most left triplet and compare it to this triplet. What do you see? Yeah, it's bigger, but look at the spacing between these ones, right? Okay, we cannot read exactly the spacing, but this looks like larger spacing and this looks like smaller spacing, this one too, right? So this likely will be a coupling constant of whatever, 7 hertz. And this one will be smaller, maybe 3 hertz. So what does that mean? Sorry, it's difficult to remember all this stuff, but in the last class, so that the coupling constant is the space between the peaks, right? So in a normal triplet, if I just have, let's say I have some neighbors. So I have this carbon has two neighbors. So it will give me a triplet. And it's a normal alkyl, carbon-carbon 3-bond coupling. Right, let me draw it like this. Right, so I have 1 bond, 2 bonds, 3 bonds. So that means 3J coupling, which is typically 7.5, 8 hertz. So we cannot really read the coupling constant there, but we can definitely see that this triplet is much more compressed. So it means it has a smaller coupling constant. And smaller coupling constant means it's a different type of coupling. It's not just a simple coupling like that. Let's look at the integrals. So what do you see? So these are the integrals, right? And so the height of this thing is proportional to the value. So if this is OH, that means that integral is 1. Okay, so that's 1 proton. 1 time H. The last one also, right? And then this one looks kind of twice the size. Where am I? Low. Okay. So this triplet of doublets looks like twice as high in the integral. So this is probably 2 protons. And that one, the triplet, also kind of looks the same height. So this is probably also 2 protons. Okay, so let's sum up the protons. 1 proton, 2, 4, 6. So I probably have 6 protons. Total. Okay, I have 6 protons. I have an OH. So let's do the mass. Question. Aha. Yes, maybe. It's something. It's a double or a triple bond, maybe. Yeah, very good. So there's probably a double or a triple bond somewhere. We could go back in our scheme. And so in infrared, alkene stretch, right? CH stretch is at 3,000, 3,100. No, so it's probably not, at least I don't see a proton. I don't see a CH stretch of an alkene. CC bond stretch for alkenes is at 1,600. 15, 16. No, so it's not a double bond. It could be a triple bond. Right? Alkene is just, so this CC stretch, double bond, is at 1,600 centimeter minus 1. So I go to infrared, 1,600, there's nothing. So it's not an alkene, it must be an alkyne, right? It must be C triple bond. The triple bond stretch is at around 2,200. Yeah, there's here a little thingy. Okay, so it could be a triple bond. Okay, so what do we have so far? We have maybe a triple bond. We have an alcohol. Okay, we're getting somewhere. Let's do the mass, right? So we set 6 protons. The mass is 6. We have an oxygen. Let's assume it's 1. Oxygen is 16. And the rest is probably carbon. We don't know how many, but this sum should be 70 U. Right, so 16 plus 6, this is 22. Carbon is 12, right? 12 times something. So let's look, 22. Yeah, we need 48. 48 divided by 12, 4. So we have 12 times 4. Right, so this is, 48, 50, 70. So based on this, I have C4H6O. Okay. What about the degree of unsaturation, right? If we look at this formula, so saturated is this, right? Is 2n plus 2. I always just remember this one. So it's not saturated, right? Because we would have 2 times 4, 8, plus 2, 10. We would have C4H10 if it was just a simple saturated alkane. So is it, how unsaturated is it? The degree of unsaturation? I never remember just the formula, so I just always see how much less. If it would be 8, it would be 1 unsaturation. If it's 6, it's 2 unsaturation. So degree of unsaturation is 2. We already had the suggestion that there was a triple bond. So yes, we have a triple bond. Or a ring, but it's very unlikely to have a ring. Well, it's unlikely given the NMR where we have this small coupling constant. Okay, so what next? So we have triple bonds, we have an alcohol connected to a carbon. Let's try to figure out if the triple bond is somewhere in the middle or if the triple bond has a proton. Does it have a proton here? Yes or no? What do you think? Yes. Why? Yes, the triplet of doublets, yes, but the last one, this is a proton. Sorry, my cursor died again. This is a proton, at whatever ppms, which is a triplet with small spacing with integral 1. So yeah, that definitely is a terminal allylic proton. So we have one fragment like this. We have this, and we have this. Okay. What are we missing? So we have 1 carbon, 2 carbons, 3 carbons. So we're still missing a carbon somewhere. So let's just draw that fragment, right? I have C triple bond C H. I have an alcohol attached to a CH2. So what's the simplest connection? Another CH2. Right? So I have my 2 fragments that I identified. With this bridge. Let's look. Does this make sense? Let's look at the NMR. So yeah, I have my allylic proton with integral 1. I have here a CH2, which has 2 neighbors. So it's a triplet. But I have this 4J coupling of the allylic proton. So this will be the triplet of doublets with integral 2. And I have this one, which is the normal triplet because it has 2 neighbors. Well, it has the OH, but that doesn't couple. So this gives you the normal triplet. And I have my OH peak, which gives a singlet, which disappears. And the formula matches, right? So I have 2, 4, 6 protons, 1, 2, 3, 4 carbons, and an oxygen. So we made it. Okay, so I put some tips. I don't know what my computer is doing. Right, so to repeat, so we have the mass at 70, which we know from the mass spec. We identified from IR that we have a broad signal at 3,500, which indicates an OH stretch. Then we also found the CO stretch, and we found that there's no C double bond O stretch. So it's not an acid. It has to be almost an alcohol, and we have this peak. And then from the NMR, we have this triplet, singlet, triplet of doublets, triplet. And we see that we have a different splitting here than here. So that already indicates allylic. And we have this 4J splitting, which is very typical of allylic protons. And so we have the formula, and then we can try to work out the segments, the functional groups that we identify, and then glue them together, take some guesses, and we arrive at the result. So yes, it is this compound, 3-butene, 1-ol. And that's one example of what you could do. And so I just, let me close this. Just pull up the, this is just from the exam of but this is not easy, right? You saw this is not easy. It's definitely not easy. But it's very important that you argue what you see and what you do on the exam. So don't just draw the molecular formula and then, if it's wrong, I have to give you 0 points. But write, I see a triplet, a singlet. This one looks narrow, so that probably means this. I see this, so that means this. So even if you don't get to the correct results, you still accumulate points, right? I know this is it's also appreciated that the French students, you have your little, note thing and you work it out and then you copy it beautifully on your exam paper. It's nice, but if it's wrong, it's wrong. Even if you write it nice, if it's wrong, it's wrong. Yeah. So try to make a habit of writing the way you are reasoning, because there is a chance that you will not solve it. But if you show, okay, I see this, I see this, I see this, then you accumulate some points here, some points here, some points here. Okay, that's an exam strategy tip. Okay, thank you. Have a nice day and good luck in the exam.